thingamajig, summation, and we're going to see that there's an infinity symbol. Since there's an infinity symbol, it goes to infinity, which means it's an infinite sum. If this was arithmetic, there'd be no solution. But since it's geometric, there's a possibility that it has a solution, and it all is based upon that R value. And I'm going to notice the fact that it is geometric because it is in the form A times R to the n minus 1. So just recognize this geometric should get you R value as well. So it's geometric, where R equals 1/2. Well, what I'm looking for with that 1/2, I'm asking myself, is the absolute value of my R bigger or smaller than 1? In this case, the absolute value of our R would be a positive 1/2, which is less than 1. In that case, it is convergent, and you can find the sum. So it's convergent. So I can find the sum. The only ones you can't find the sum of it is if it's bigger than 1. If the absolute value is bigger than 1, then it's divergent and you can't find it. But since it's convergent, we can go ahead and find it with the summation formula where we have, let's go back to black. Our sum is going to equal our first term over 1 minus R. But the problem is here, our first term really isn't a sub 1. Because our first term when we're in our summation formula like this is whatever our lower limit is. And our lower limit here is -1. So my first term is going to be what happens when I plug in that -1. So my first term is going to equal what happens when I plug in that -1, which would be 3 times 1 over 2 to the -1 minus 1, which is going to equal 3 times 1 over 2 to the -2. And you have to remember what raising a power to the negative is. All it tells you to do is take the reciprocal and then square it. So this would be 3 times 2 squared, which would be 4 times 3, which equals 12. So my first term is 12 over 1 minus my R value is 1/2. 12 divided by 1/2 is going to equal 24. That is why the answer is D, 24, and it is not A, no answer. If this right here would have been 1.5, then it would have been no answer. If this would have been arithmetic, it also would have been no answer. This just fit into that realm of it being geometric and my R value is less than 1, or the absolute value of R, I should say. All right, what questions do we have from the homework? Yeah.
3.
Number 3. So that.
Yesterday you told us 6, and the answer keeps.
Oh, that was this class. Okay, yeah. The answer it is 8. I thought so. 3 and 4 were both football questions, and one was if we played 2 games where they can tie. And when I didn't look at the question you actually asked, you just said the football one, and I assumed it was that one. But it should be the 2 times 2 times 2 equals 8, because in the first game they could win or lose. Second game they could win or lose. Third game they could win or lose. So it would be a series of a 2, a 2, a 2, and it fits the fundamental counting principle because I can pick one of these, one of these, one of these. So that just means you multiply the totals, which would equal 8. So number 3 should be 8. Other questions? Questions going once, twice. Make sure you know this stuff because we're going to go into combinations next. So don't be sitting there with one that you kind of know how to do, but not really. Okay, then we will go on to combinations. Combinations and permutations, they go together like peanut butter and jelly, yes. Whatever it is. But they go together. The whole idea is we have to decide which one we're going to use a combination on and which one we're going to use a permutation on. And the big problem is in English, we misuse the word combination all of the time. So we have two uses of combination right here. The first one says my fruit salad is a combination of apples, grapes, and bananas. The thing about that combination is I don't care what order the fruits are in. You could also have a banana, grape, and apple one. You could have a grapes, apple, and bananas one, and it's still the same fruit salad. It's all mixed up. This is the proper use. So this is, in fact, a combination problem. The second one says the combination to a safe is 4, 7, 2. Well, this time we do care about the order. You can't just type in 724 and it's going to open. It has to be exactly 472. So although in English we say we have combination locks, you in fact have a permutation. So a correct statement there would be you have the permutation to the safe is 472 because in permutations order matters. So in precise mathematical language, when order doesn't matter, we're going to call it combination. When order does matter, it is called permutation, which is why on the bottom it says we should call every lock a permutation lock because order definitely matters. If it was actually a combination lock, it wouldn't matter which order you did the 4, 7, 2, but it definitely does when you're doing your locks. So we're going to boil these first two sections into these this matrix of sorts. The only thing that's missing on here is going to be that fundamental counting principle, which you do have to still use. Okay, permutation. Order matters. Order matters. What order you have something in definitely matters in a permutation. In a combination, it has no effect, so it does not matter. So when you're doing these problems, you just have to ask yourself, does order matter or does it not matter? With permutation, we already did our notation. I'm going to add a second notation to it. And our permutation notation is P parenthesis N R, where N is the total number of things I'm pulling from, and R stands for how many of those items I actually want to pull out. On your calculator, you might see it as N, P, R, just like that. That is still the same permutation formula. For combination, there's actually 4 different ways you can write it. You can write it pretty much like a permutation where you have a C instead of a P. So we have C parenthesis N R. We can also do it the same way we did the permutation in the middle there, where we just have our N on the left-hand side, cap C in the middle, lower or sub R at the end. And the final way is we can do it without even using a C. You'll oftentimes see combinations as just N over R surrounded by parentheses. That stands for combination as well, even though there's no C. For more or less, for this beginning section, we'll just use the first ones of those, but you can list them as any one of those 3. When we get into our next section of this, we might move to the combination, the one far to the right, where we just do N over R. The middle one's more or less your calculator button that matches up with your permutation combination ones. All right, our permutation formula is going to be N factorial over N minus R factorial. And since order makes a difference in permutation, combinations are going to have far less numbers associated with them. But the formula is going to look very close, except we're going to eliminate some possibilities. So we're going to have N factorial over N minus R factorial, which looks the exact same as my permutation one. The only difference is we need to eliminate those ones where order actually mattered in permutation. So we're just going to multiply on the denominator by R factorial. So the only difference between combination and permutation formulas that are factorial on the bottom. Otherwise, they're both the same formula. Now, notice we have two new formulas. Right? We have permutation, we have combination. That's two more formulas that are on top of all the other formulas you already have to know. As I've said, I will not let you use a note card on this test, nor will I provide you a bank on the test that says, these are your permutation ones, these are your these. I will not provide these formulas for you. You have to know these. So right now is a good time to start practicing all your formulas so you don't get stuff mixed up. Your whole test on this is basically based on can you know these formulas and where to apply them. So now is a good time to start memorizing them and making sure you know them. Handy way is just to have a note card that just says permutation on the back, has the formula, maybe some other facts that go along with it. Note cards are great for this one for studying. All right, some examples. Solve using either permutation or combination. So that means we need to decide, does order matter or do we not care about the order? The first one says a 3-person committee is needed to study ways of improving public transportation. Let's stop there. A 3-person committee. Do you care if you're committee number 1, committee member number 2, committee member number 3? No, we do not care about order in that one. There is no hierarchy in a committee. It is just 3 people that are selected that form up that committee. So order does not matter. So just from that first sentence, I can go, does order matter? Nope. Which means we're going to use a combination. All right, let's continue reading. Ooh, that was an A. So we're choosing a 3-person committee, and it says how many committees could be formed if we had 8 people on the board right now. So that means our total pool of candidates, our N value is going to be that 8. We have 8 to choose from, and our R is how many I'm going to choose from there. Well, it says we're doing a 3-person committee, so I must be choosing 3. So writing this down, we have a combination where we have 8 choose 3. Which will lead to the formula 8 factorial over 8 minus 3 factorial times 3 factorial. And I'm going to preface this right now. This can definitely be a section on the test that says you can't use your calculator. This one, you do not need your calculator to actually solve. So you might want to take notes on this if you're not sure how to solve this by hand. Well, if I was solving this by hand, I would just reduce stuff. So I had 8 factorial over 5 factorial times 3 factorial, which equals 8 factorial. Well, let's reduce the 8. I'm going to go 8 equals 8 times 7 times 6 times 5 factorial over 5 factorial times that 3 times 2 times 1. So I reduce this a very specific way to show myself, well, this stops at 5 factorial and we start up at 5 factorial here. So I can now cross out my 5 factorials. Well, that leaves me with 8 times 7 times 6 divided by 3 times 2 times 1. Well, we can go one step further. We can say this 3 times 2 equals 6, so I can cancel out the 6 up there. All I'm left with on the bottom is 1. All I have to be able to do in my head is multiply 8 times 7 to give me 56 ways. So once again, you are fully responsible to be able to do that in your head, or on your sheet, I should say at least, that you can write it out. So know how to simplify these. All right, that's 56 ways. We're done. Moving on. 12 students help with a project. The director needs 3 telephone solicitors, 4 door-to-door solicitors, and 5 magicians. And how many ways can these jobs be assigned? This one gets a little trickier. We kind of have to treat each one of those as their own entity. We have to look at telephone people, then we have to look at the door-to-door, and then we have to look at the 5 magicians. If we look at them separately, does it matter which telephone person you are? No. Does it matter which door-to-door person you are? And does it matter which magician you're going to be? Nope, you're just one of 5, a nameless member of society. So your order does not matter. So no, it does not matter, which means we're going to use a combination. And in a problem like this, we're going to break it up into 3 categories. We're going to have a telephone category, people on a telephone. We're going to have our door-to-door people. Let's call them door people. And finally, we'll have our magicians. Let's call it magic. We have 3 categories: telephone, door, and magic. And it is a combination. So under telephone, I start with 12 people. We have 12 students. So we're going to have a combination formula where we have 12 choose. How many did I say we have? We have 3 telephone. So now I have my telephones stocked. All right, for the door, we're going to also have a combination formula. But what 2 numbers am I going to fill in that combination thing? Be careful on this one, Alex. It would be 9. Yep, it'd be 9. Choose 4. It can't be 12 anymore because we already have 3 people on the telephone. So we're going to have 12 minus 3, which gives me that 9. Choose 4. And finally, the magicians, well, using that same logic, we're going to have 9 minus 4, which is going to be 5. Choose 5. Yeah.
What if, say you started with magic, door, then telephone, then it would be for door 7 and 4.
It'll still work out.
Okay.
It'll be the exact same. So what Logan's saying is, what if I start with magicians first? What if I do 12, choose 5? Then I would do 7, choose 4, and then finally I'd have 3, choose 3. You will come up with the exact same answer. Doesn't matter which order you do these in. It doesn't matter whether you pick your magicians first, your door people first, or your telephone. You'll come up with the exact same answer. So don't worry about picking them in the right order. Now all we have to do is multiply what we get from those together. So it's going to look something like this. So 12, choose 3. We're going to have 12 factorial on top. We're going to have 12 minus 3, which is going to be 9 factorial, times the r value, which would be 3 factorial, times our next combination. Our next combination was the 9, 4. Well, if we have 9 and 4, we're going to have 9 factorial on top. 9 minus 4 is going to be 5 factorial down here. My r value is 4, so it would be 5 factorial times 4 factorial. Finally, we're going to have 5 factorial over 5 minus 5, which is 0 factorial, which actually equals 1, times our r value, which is 5 factorial. And we'll see right away those 5 factorials cancel out, and we're just left with 1. And that's going to happen every single time if our r and n are the same value with the combination. Because what they're saying is, if you have 5 people, how many ways are there to tell all 5 people they're clowns? And that's just, or magicians, that's just one way. You just tell them they're magicians. All right, so this will always be 1 if your r and n are the same. You could go further simplifying this, but this is going to be a calculator portion, so you could cancel out your 9 factorials if it helps you put it in your calculator. So now we could put in our calculator as 12 factorial over 3 factorial times 5 factorial times 3 factorial. And you should, when you plug this in your calculator, you should get some value out. Let me get that. Oh, yep. I usually put those in order. I usually go 5, 4, 3, so I don't do that. It's like the one time I didn't. But you'd end up with 27,720. So that is not one that I'd put on and you have to do in your head. Or it could be fun to make you do that too. Maybe I'll put it on there. All right, our next one. We have 50 people purchasing raffle tickets. 3 winning tickets are selected at random. If first prize is $500, second prize is $100, and third is $50. How many different ways are there to be awarded? Do you care what place you get? Yeah. You should be, if I tell you, Lizzie, you got first place, here's your $50, you'd be like, wait a minute. Order definitely matters in this one. Yes, it does. Does order matter? Yes. So we're going to use permutation. Our permutation equation, we're just going to have P is, well, we start with 50 tickets purchased, so our N is 50. We're choosing 3 of the tickets, so it's 5 pick 3. And that's going to be 50 factorial divided by 47 factorial times 3 factorial. Once again, if you wanted to, you could reduce this to 50 times 49 times 48 times 40. Oh, I'm doing a combination. You're right. So we're just over 47 factorial, so we'll just end here, and we'll be over 47 factorial. We can go ahead and cross our 47 factorials out, which will give me 50 times 49 times 48, which maybe you can do that in your head. Maybe you could write that off, but it's probably just easier to come up with the is going to equal our 117,600. Is that right?
Yeah.
Someone typed that. Okay, it just seemed wrong. I don't know. Something felt wrong about that with the 9 and the 8. All right. Other people checked and it's right. We're good. This last one, identical objects. Do not just think because it's buried at the end of the lesson that it won't be on the test. I guarantee you it will be on the test. There will be at least one problem on the test that looks like this. I could say that because I know people are going to still get it wrong, even though I tell you it's on the test. It is a super easy process to do. You just have to know how to do it. So we're talking about how many different ways are there to arrange Mississippi. How many different ways are there to arrange Mississippi? The problem comes in with the fact that I can't just swap S's. There is no S1, S2, and I flip it and it's a different word. If I just move these 2 S's, it's still the same word. I didn't change it at all. So I don't want to count that. I don't want to count anything that actually is the same word, just an I flipped or S's flipped. So instead, we have to get rid of all the ones that would be duplicate ones based upon that, which turns out it's a pretty simple process. Combinations with sets of identical objects. You can read all that, but I always find it easier to do an example first. So we have Mississippi. That N value that's on top is going to be how many elements you have. So our N in this one is how many letters I have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So our N equals 11 because we have 11 letters. So the top of my formula is going to be 11 factorial. Now what we're going to do is we're going to figure out how many of each element I have. For example, we're going to look at our M's. And I'm going to count how many M's I have. Well, I just have one M up there. So we'll put a 1 for M's. Then we'll go down the list. Now we have I's. How many I's do I have? I have 1, 2, 3, 4 I's. Maybe I'll put a line under this because we're calculating something else. M-I-S. We got S's. We have 4 S's. I already tackled the I, the S, the I. I just have to tackle the P's, and we have 2 of those. It's always a good idea to check. 4 plus 4 is 8, plus 2 is 10, plus 1 is 11. I tackled all the letters. Now all I have to do is take all of those numbers, and on your own you'll realize which ones you don't need to put. But we're just going to put 1 factorial times 4 factorial times 4 factorial times 2 factorial. And our result is going to be the total possibilities of 11-letter words that we could spell with that with no duplicate words. So we're going to have 34,650. There's just one more problem we're going to do. It's going to go really quick. For some reason, people really struggled with this last year. Even though that next question, I don't even have it on here. I'll put it up as the blank, but I'll read through it with you. A lot of people struggled with it last year, but it is the exact same premise as that one with the phone, doors, and magicians. This one says a company employs 9 male welders and 7 female welders. And then it says they want to pick a committee where they have 3 male workers on the committee and 2 female workers on the committee. Once again, you're going to ask yourself, do I care which committee member I am? Well, besides male or female. But if I'm a male, I don't care which one of the 3 spots I get as long as I'm on the committee. So that means it is a combination. Order doesn't matter. And we're going to treat it as 2 separate things. We have a male portion of the committee, and we have a female portion of the committee. The male is going to be 9, choose 3 of those 9 guys to be in the committee. The female is going to be, correct me if I'm wrong, is there 7? I don't have it up here. Is there 7 females? Okay, and we're choosing 2 for the committee. So our females is 7, choose 3. All we're going to do is multiply those together. I'm going to let you write those out and solve it, but you should get an answer of 1764. Make sure you can get that answer. Otherwise, the rest of the homework is pretty straightforward. Just make sure when you get to the combination, permutation, fundamental counting principle that you're using the correct one. I do want to talk really quick on the fundamental counting.